So we're going to process this corpus here. So a corpus in computational linguistics, or NLP, is a collection of documents. NLP, natural language processing. So typically, a collection of documents. And this is an increasingly growing data set on academic papers published around COVID-19. And they are made available by the Allen Institute for AI, which is, I believe, an NGO devoted to blue sky research in artificial intelligence. And what we're going to do is we're going to write Python code that takes this data, cleans it, and in the process we're going to understand a bit better this data, and then we're going to convert each of these papers, or at least a small subset, because as we will see, it's a massive data set. We're going to convert them into a numerical representation, which then can be processed by a machine. And what this means is that in the specific use case that we're covering today, we will be able to compare them. So we will build representations for these documents, and these representations will be projected in a vector space. And we're going to compute the similarity between each of these documents by computing some distance metric between their corresponding vectors. And then once you have a way to measure how document A is to document B, effectively you can have a system that will retrieve similar stuff. So if you are consuming papers that talk about a certain aspect of COVID, or maybe you are interested in the effect of COVID on pregnant women, so maybe several of the papers that you've been reading, that you will have read, they will share the vocabulary, certain expressions, linguistic patterns, so you can take advantage of that, so that the next paper that you read, the system could recommend something that goes, is similar to the topic. Yes, so there's a question. We all should have a link to Google Drive. So this is also this can also be made public. The only difference will be that if you get the link, you will. There's a link here saying something like add to my drive or something. That means that by default you're not the owner of Google Collaboratory notebook. So if you have a public link, you can access, but in order to edit that and actually run it with your Google account, you have to add it to your Google Drive. And we don't have this option here because it's already in my Google Drive, but it would be as simple as that. And the reason why this is also necessary is because we're going to load data. So these two spreadsheets are going to be loaded in this notebook. So in order to access my own Google Drive from this environment, this environment needs also to be linked to my Google Drive. I hope that makes sense. Okay, so there are a few things like Python stuff that we haven't seen in the webinars 1 and 2, but because we already know a lot about Python, we won't need to spend a lot of time on them. Hopefully they are self-explanatory and clear enough as we move forward. And specifically, what we will get out of it, we will learn how to write functions. We'll learn how to traverse a directory. Actually, well, not necessarily because we only have 2 files, but we could. We're going to talk a little bit about external libraries, so how to have access to already written software that's been written by other people that we can incorporate into our program in one line. Transform text into numbers, and then compare the numerical representations of these documents. So there's a little bit of text processing, a little bit of data science, and a little bit of Python. So a mix of everything. And as I say, so this is, of course, it's better if either you have watched or attended the 2 previous seminars, or you're somewhat familiar with the basics, but I'll try to make it as accessible as possible. Okay, so I guess we can get started now. No? So this is a notebook for building a recommendation system. And the definition in Wikipedia about recommender systems is this. It's a subclass of information filtering system that seeks to predict the rating or preference a user would give to an item. So basically, having a way to estimate how much am I going to like if I have consumed items 1 to 10 or 1 to n, how likely am I to like item n plus 1 if it's it's a recommendation from an automatic system. And as you know, we are we use these recommendation systems. They are embedded in our daily life for movie recommendations, people to follow, playlists that we're likely to like, and so on. Okay. And as you can imagine, recommendation systems is an area in itself. There are many different approaches for building algorithms that recommend you the best stuff. But it's difficult because the success metric, so what is actually considered to be the best, is not clear. And it depends on a lot of factors, starting from the domain. So again, no, I'm no expert, but I would assume that some of the principles that apply to video game recommendation will probably not apply to music recommendation or to book recommendation. Turns out when I was doing my PhD in Barcelona at Pompeu Fabra University, I collaborated quite a lot with the music technology group, and we started a line, a direction on improving music recommendation, either because we try to make it better, or because we try to make it more self-explanatory. No, so to provide explanations in natural language about why, if I was listening to this song or this artist, why would I get this recommendation? And we did some text processing from web data, and we built some graphs and used these graphs to explain, to make music recommendation more explainable. And turns out that the timing for this webinar is very, so this is a shameless plug, but I mean, I needed to say it. So Friday, there's the first workshop on natural language processing for music and audio. I'm co-organizing this with a good friend of mine who was doing his PhD as well back in the day at UPF, and other colleagues from industry. And it's free. So if you're interested in what are the latest advances in this synergy, right, between music recommendation and natural language processing, by all means, go on registration and follow the process. It's free. The conference called ISMIR is not free, so the conference where this workshop is happening is not free. But if you're attending only the workshop, then it's free. And we've got a very good lineup of invited speakers from Google Brain, Harvard Music Lab, Amazon, and so on. So yeah, definitely. So this also shows that this is an actually a very hot topic. So this is the first workshop of its kind that's been done in music information retrieval and music development and so on. Okay, so this being said, again, no. Usually when we deal with automatic recommendations, there are two major approaches. There are others, and again, this is as far as I know. One of them, the most typically used, is collaborative filtering. So here, here you estimate how two users are related based on their shared likes, in a way, no? So if their habit is to watch movies of a certain type, then surely a third movie, if they share the same items in their history, it's likely that a new item that's watched by user A is likely to be appealing to user B. And this is, as I say, probably one of the best known approaches, especially because you really don't need to do anything about the content itself, right? So as long as you have information on who watched what, or if you have ratings and you know, a star system or a ranking, then that's even better. But even the fact that someone watched something versus I see that share the link, which is going to be here. So I'll just put it right here. Okay. So as I was saying, no, so you don't really need to do anything with the content of the items themselves, because the fact that they are shared items between users is already a good enough signal. There's another approach, and this is coming from this excellent and very popular Medium post on movie recommender system. So this is content-based recommendation, and this is what we're going to look at. So here, what we have is one single user that consumes one single item, and because we know this item is similar to this one, then we can recommend it. And this is where the challenge is well, the challenging bit for processing unstructured data, like images, audio, movies, or in our case, text. So here we don't really have access to who else watched this, but it doesn't matter, because the only thing we care about is whether this is similar. As long as they are similar, it's very likely that this is going to be a good match for our user. Okay. Now, going into the specifics, you will probably notice that there's much less Python code at the beginning of the webinar now than in the previous two sessions. But it's also the nature of a data science project itself, to have a good understanding of why am I doing what I'm doing, where do I want to get to, what is going to be, what is my success criteria, and also when am I going to consider I'm doing the right thing, and when will I know if I'm failing? And here, with a lot of this, we don't know. The only thing we will be able to look is at the similar papers that our bit of code will return, and whether it makes sense to, given paper A, to get recommended papers B, C, and D. So again, let's have a closer look at this publicly available data set, because that's what we are going to process. So as you can see, the latest release is from October the 12th. So that's from yesterday, 5.2 gigabytes. So I have a much older version of this, and I think it's good enough because it's a massive data set, and as you can see, it keeps growing. And just as a curiosity, and in the early days of the pandemic, there was a lot of activity in Kaggle, which is a data science competition platform, on processing these papers. And Kaggle basically is a platform where you enter data science competitions, and sometimes there's a prize pool, sometimes not. And here they release this corpus for people to do some exploratory analysis on the COVID-19 papers. So here, what we can see here is that there was a lot of analysis on who, where, the citation correlation, and so on. And I wanted to show, let's see if I can find it. Yeah, literature clustering. No? So this is something very cool, and it kind of correlates with what we are doing, because in the end, so this is a nice 2D visualization of a space where each data point corresponds to one paper, and the different colors correspond to clusters. And what these clusters mean is that there's something similar between these guys that make the clustering algorithm, whatever it is, assign them to the same cluster. Sometimes you will see that the cluster here in dark green, well, we've got a few seemingly outliers here. These clusters seems to be very well defined. You can actually go to a live browser where you can get all the metadata just by browsing here. Technically, we could do this with our own vectors as well, our paper vectors as well. This is nothing more than a two-dimensional projection of a higher dimensional projection, which is something that we're going to look at now. So yeah, a lot of interesting stuff from the data science point of view happening in the last months. And now let's talk a bit about the original data set. So wrote a bit of a statement here. No, so an important element in all instances in data intensive coding is wait for it, cleaning data. And if well, I guess we have probably a large number of people attending the webinar who are dealing with data in one way or another, or are just interested in how this works. But this is something where a task where you practitioner of any discipline where data is a major component, then of course you need to spend time on it, because data might be incomplete, obsolete, incorrect, duplicated, etc. Especially the more human intervention we have and the less you can automate things, the more prone to error the data sets that are result from that human intervention are. You will very often read, I'm sure you will see a million Medium posts or Twitter threads or something on data cleaning, but there are some courses that use other terminology, data preprocessing or even data auditing. I believe this comes more from the databases community, but don't quote me on this. So now what we're going to look is how each of the papers look like in the original data set. And like I said, no, in just like in a cooking lesson, we're going to fast forward into a more manageable format. This is a decision I made because otherwise probably most of the time spent in the webinar would be about processing the original data format. I think it's useful but not very exciting, and there was the risk to not have enough time to spend on the natural language processing, or at least the basic text mining bits that we were doing. So yeah, let's have a look at what each document looks like. And after that, we'll fast forward and we will work with a cleaner version. So I've got a text editor here. And the original data set has a lot of files like this. So you've got an ID, this one, .json. JSON is a data format that's typically used in APIs and computer science in general to move data from one place to another. It's a very well-established standard. And if you know Python, or at least if you're not super unfamiliar with Python, this is something that should look familiar to you. Because at first glance, it actually looks like a dictionary where each key is a string, and then the values can be other stuff, other dictionaries, arrays, or lists, strings themselves. But as you can see, it's not very coding friendly, especially if we're not, like, if we haven't written thousands of tens of thousands of lines of Python code before. So it can be a bit intimidating. What we can do to get a better idea of how this data set actually looks like, there are, I did something, yeah. There are a few online JSON visualizers, because and these are useful online tools that help you to have a better idea of the hierarchical structure of a JSON object. JSON object is just a Python dictionary or a list of Python dictionaries, but because dictionaries can be nested with at as many levels as possible, sometimes it's easy to get lost, even with this nice tabulated and nicely tabulated format and syntax highlighting and so on. It's really sometimes difficult not to remember this bibref, which is simply a reference in the paper where it is pointing to. No. So this particular website, you just come here, copy your JSON object, and it will format it in a very similar way than the old school XML or HTML format. No, so you will have here you've got the root is the JSON object with the paper ID, and this is important because we're going to use it later on. And a bunch of fields, metadata with a title and the string with the actual title of the paper, author, so one nested dictionary per author. Sometimes we have a middle name, sometimes not, depending if they are, usually if they come from an English-speaking country. The body text, where we have one nested object per paragraph. And then in each paragraph, we have site spans. I mean, it's quite convoluted, no? So that's why I said I spent a bit of time, not much, to makes life a bit easier for us, especially in the context of this webinar, and cleaned it up a bit. And we'll see now what the clean format. The clean format still needs to be loaded in disk, in memory, still needs to be processed. So there's still going to be a little bit of data auditing and data loading on our side. JSON stands for JavaScript Object Notation. Turns out the syntax fits 100% with Python, so we don't need to learn anything new. And the JSON format was invented by the famous scientist Jason Statham. It's great that I can't see any faces because it would be a lot of face palms. But I just couldn't resist. And be aware, this is not the only joke in this seminar. Right. So after you recover from the laughter, we can look at the data set itself. I got it here, right? So this is my Google Drive folder where I have a bunch of pictures that I in the end I didn't use them because I'm loading the photos using this small code that loads a photo from an online source. I decided to do it like this because in the same way I could leave as an HTML comment the actual source or give credit to the source of the image. But here we've got two files, abstracts and titles, which look like this. So abstracts is a CSV file, a spreadsheet with two columns. Actually, I think it's better to look it like this. Yeah. So it's the same files. Abstracts.tsv, which stands for tab separated values and titles. And here the process from going from JSON to this tabular format data made it so we have the data in this form. For each paper ID, we have one line for each of the sentences in the abstract. Okay? So for paper ID 5B889 and so on, we have 1, 2, 3, 4, 5 sentences in the abstract. And for the same paper ID, we have one line in our titles file, which is the ID, a tab, and the title, right? So we've got two files, one of them paper ID per abstract sentence, and another one paper ID mapped to the paper title. And what we need to write is some Python code that takes these two files and loads them into a manageable format. So let's see how we would do that. I did this already, and we did this in the previous webinars as well. So here, the only thing we do is run this snippet of code. This will allow us to have access to our file system in Google Drive. And you can check whether that's actually happening, because once you do that, it will prompt you, give you a link, you take the link, it will give you a token, a small password, you copy paste it here, and you will have your drive mounted at this location. So you can go here and check that if this folder is available, this was successful. And then you can expand this, and inside the My Drive folder, you can see the contents of your own Google Drive. Okay? Okay. So now what we can do is get the path to this folder. Now, how do I know the path to this folder? Because it's like content, /content/G drive /my drive /Cardiff, da, da, da. So, well, I know because I know, but in case you weren't sure, there's a way where you would just expand, navigate through your Google Drive until the folder that you know you want to use. This one, right click, copy path or copy route, or however it's in English, and then you paste it. And now we know for a fact that this variable data dir contains the path to this folder. And from there, we will have access to all the files stored here. Now, what we do is take this data.dir directory and create two strings, abs path for abstracts and tit path, title path for titles. And we simply concatenate. Actually, we have a problem here, right? So we're missing the last slash, the trailing slash here. This is not going to be treated as a subdirectory. It's going to be treated as a whole file, and it would break. So we need this guy here. We could do it in a better way, but to not overcomplicate things, let's do it like this. And now we have our proper path. Okay, so far so good. And now we're going to write a function. We're going to write a function for loading the data. We haven't seen functions before, so I'm just going to leave, I'm going to finish my coffee for half a minute and leave the anatomy of a function that converts Celsius degrees to their Fahrenheit counterpart. Have a look at the anatomy of a function in Python, see if it makes sense to you. This is apparently the formula for converting Celsius to Fahrenheit. I don't know why. Eric knows, so if someone is curious, after in the QA, we can talk about this. I don't have a clue why this is the case. So even without, as you can see, the syntax is quite minimalistic, so it shouldn't be too difficult to figure out what this function probably does and what the keywords and statements mean, even if this is the first function you've seen in Python in your life. Okay, so Python defines functions with the def keyword, and then we have a name which we decide, and then round brackets, and then we have an input argument, and this input argument can be one or more. There's quite a lot to say about this, but this function is simply a piece of code that's going to take one input and it's going to return one output, period. Now inside that function, that input is going to be transformed in a way that defines the correlation between the inputs and the outputs, just like a mathematical function. The keyword we use in Python for returning values is return, and it's not mandatory. We can have functions that don't return anything. In Java, this is they're called void functions. But I can say simply, let's say I'm here. So if I define a function, greet print hi, and then I say greet, of course, this is fine, no? This is not returning anything. So if I say value equals greet, it's none, because the return statement is missing. So this function, by default, instead of breaking the Python code, is returning a non value. How we can, the hi is printed because when we call the function, the code inside it was printed, right? Not because we have this print statement here. So this is important, okay? Now we have this function here. It's the same, just instead of Celsius to C to F and so on, and instead of having the whole all the computation happening in one line, we have one line for doing the math assigned to a variable, and then we return the variable. I just think this is a bit more self-explanatory, although the variable result maybe the name result for that variable is probably not the best. And apparently 17 degrees Celsius is 62.6 Fahrenheit. Okay, so now that we know what a function in Python looks like, we write a function for loading these two guys, titles.tsv and abstracts.tsv. Okay. So before I go through the code, I'm going to say why I wrote the code the way I wrote it. There's one issue that I realized after cleaning the data, but I left it like that because it really shows how complicated these data cleaning processes can be. So turns out that even after cleaning my data, I have entries for papers for which I don't have a title. Maybe there was the title field in the JSON object, but then it mapped to an empty string. Something happened, right? We don't care about what happened. The only thing we know is that we have incomplete data. And I know beforehand that my paper retrieval system is going to operate at the title level. So I'm going to input the title of a paper, and it will show me similar papers to the paper with that title. But if I don't have a way to record the titles of the papers, I cannot do anything with those papers, even if I have the abstract and all the rest of the metadata. So this is a key field that I need for building my application. This means that I will do a very easy workaround, and I'm going to skip all abstracts for which I don't have a title. So what I'm going to do is, first, I'm going to build two dictionaries, one for titles, one for abstracts, where the keys are going to be the paper ID in both, and then the value is going to be the string for the abstracts dictionary, and the string for the titles dictionary. The way I do this is with again, not verbose and probably inefficient, but that's the point of doing well, code that's hopefully understandable enough and not obscure. You see, I got quite good feedback from the first two webinars from people appreciating the fact that we were stopping into all the details, and we were not saying, yeah, I will not get into details on here. You just import this library, it does this, here's the result. So what we do is we define two dictionaries, abstracts and titles. And then we are going to write a for loop to iterate over each line in our files. The open statement in Python by default operates at the read in read mode. So remember, files, we could open a file for reading it, we could open a file for writing it. So if you open a file that's already in your hard drive with this format, you're going to overwrite it. So you're going to wipe everything that file has, and you're going to write from scratch whatever it is that you writing it in this loop. So this is kind of a risky thing to do. But this is equivalent of writing this. So the mode by default with the open statement is read. Now, files operate like lists, in the sense that, and if you have questions about this afterwards, maybe if we have time we can talk. So they operate as memory efficient lists. This means that we can iterate over them. So we can write a for loop on top of an open statement, and by default this aligned variable that we're declaring in the for loop is already going to correspond to each of the lines in our file. And if again, I'm not going to talk about this memory efficient thing, but it's an interesting thing to know. Okay, so abstracts file. So let's go back to the abstracts file. It's this guy here. I am here. What I'm doing is I'm searching by something called regular expressions. So if I do, this is way out of the scope here, but I want to double check that I do have the tab key, and the \T is the tab character. I think for Windows must be the same. And this is what we have, right? So a spreadsheet, two columns. First column is the paper ID. Second column is the one of the sentences in the abstract. And if I wrote my code for producing this file well, this must be in order. So this must be the first sentence of the abstract of this paper. This must be the second one. This must be the third one, and so on. So what we're going to do is, a nice property is that we're going to do the line, we split it by the tab. What this means is all strings, the string type in Python, just like any other type, has their own method. So they allow us to call different methods on which do stuff on them. So there are two things that we need to know here. One of them is methods. So basically, this is like calling a function, which is it translates to it will do something on that string. It's different to accessing an attribute or a property, so which would not have the square, the round bracket. So if you see Python code where you have an object like a string, a list, or something, dot something followed by these guys, this means this is a method. So this is doing something on this. Maybe even just retrieving some information from this object, but it's doing something. Whereas if I don't have this means that I'm accessing some kind of information I would have here. I don't know, to put it, maybe to give an example, imagine a video game and you've got a shooting video game. So you've got the spaceship, no, and the enemy spaceships. So every time you click shoot, there would be a method called shoot being called like this, right? But then you see on screen how much life you have in the health bar. So this is probably, so you would have the shoot method, so it's spaceship shoot, and spaceship health, right? So this would tell the program to run an action, and this would tell the program to retrieve the current health, right? So this is the main difference between methods and attributes. Okay. So this being said, we call the split method on the tab character. So I'm going to Control C here because what I want to show is how the split method on strings operate. It basically splits them. Right? So you pass the character or sets of characters you want that string to be split at, and the result is a list where each element is a string until the splitting criteria that you had. So of course, if I do this and I write a space here, the result is the same. But split by default operates with on white spaces. So actually, if I don't write anything, I get the same result. Because my file is tab separated like this, when I do align.split on the tab, and I know for a fact that all lines have two elements because it's a two-column spreadsheet, I can unpack those variables in the same line. So here I could say Luis, Eric, Carla equals this, and this would work, right? It would work, it won't complain because the result of this line is three objects. If I do this, not enough values to unpack, expected 4 because this is what I told Python to retrieve, but got 3 because this was the result of this line of code. Okay. Of course, you can always do this. This you can always do. You can always get the values of your splitting functions into one variable, and this is a list where the first element is Luis, the second element is Eric, and the third element is Carla. And so we access Eric here. Remember that in Python, the indices, we start counting from 0. Okay? Okay. So now that we know that we have the paper ID and the sentence for that abstract, we do the following. We check if the ID is in the abstracts dictionary. Of course, for the first sentence, it will not be there. So we create an entry for that paper and assign the first sentence. Easy. So for the first sentence, I will create this key and assign this string. But then when in the second iteration, this line I already have a dictionary with this key. So I don't want to run this again because this would be this would be overwriting the previous line, right? So what I do is I do use the increment operator, so plus equals, and the same sentence. What this means is it's going to concatenate every time I find a sentence, it's going to concatenate the current sentence to the string I already had, which is going to be the first sentence in the second iteration, the first two sentences in the third iteration, and so on. And then once this is done, so At this point in the code, I have a dictionary of paper ID abstracts. Now, here I do exactly the same, but I can't do that. So this unpacking of two elements, I cannot do it because I have seen that I have some cases where I wouldn't get the two elements because this is an empty string. If I split by tab here, I will only get one element, and then Python will complain because it will say that it's going to expect two, and here, no, if I did this, it's going to expect two, but actually in that case would only be one element. So I assign to one variable, so it's like exactly the same as the X example before, because then I can check if the length of this variable is 2. So then this is like a sanity check, and this would mean that I would effectively skip this line because the length of the values variable would be only 1 because I would only have the paper ID because there's no title here. Now, one thing I have here is the strip method as well, because I am going to search for paper titles. There's a quite annoying thing when you deal with text files, and it's that you always have as last character, you see, the last character in this line is not the Y in pathogenicity. It's this, the new line character. Like so, in Linux, it's denoted as \n. I think in Windows is \r\n or something. So if I search by new line characters, you can see that it's at the end of all lines, which makes sense. But the title should not include this guy here. It should only go until here. So the way I do it is I iterate over each of the lines in my title file. I first call strip, which what strip does. Actually, let's have a look. So let's define one simple string, hello, and then call strip, and then we can do help on this guy, and we will get the Python documentation for this function. Strip returns a copy of the string S, so in this case, S means hello, with leading and trailing white space removed. If characters, so this optional parameter I can pass is given and is not none, which is the default, remove character in chars instead. What does this mean? This means that hello strip, and remember this is a method, so because it's a method, I need to put the two round braces to tell Python that this is something that is expected to run an action on this object. And the result of this is hello, but without this guy. And I could do this as well. And if I do this, this is the result, right? So now we're not removing the white spaces anymore. What we're removing is whatever character we pass as input to the strip method. So because the / character like this is also white space, it qualifies for being removed with the strip method, okay? This is just to remove the new line character. And now for each of the titles, for each of the paper IDs for which I have a title, then yes, now I can unpack because this is ensuring that I will never have a values variable with a length different of 2, which means I can unpack and then I can assign for each new line a title ID to the actual title, right? And there's no need to do any increment here because I know that in my source file, I only have one distinct line for each distinct paper, okay? So now we have two dictionaries. One dictionary is abstracts, the other dictionary is titles. But because we have had the misfortune of having to skip some titles, it turns out that we don't have the same number of elements for the abstracts and for the titles. We probably have more abstracts than titles. So the way we're going to work around this is we're going to do one extra step where our function eventually is going to return two data structures like this, two lists instead of dictionaries lists, and the reason for this is we want to keep to have a way to easily find titles and abstracts by position in a list, because this is also what we're going to need when we compute the similarities between them and so on. So how do we do that? Well, now it's very easy because we can simply iterate over each of the titles, because this is the source data for which we have the list. This is a sanity check. So we check that for each of the papers, if I have it in the abstracts dictionary. If I do, then I keep track of the abstract and the titles for that particular paper ID. So remember that you can access a value in a Python dictionary by key. So if I have the paper ID XYZ, if I pass XYZ to my abstracts dictionary, it will get me the abstract for XYZ. And if I do the same for the titles dictionary, it will give me the title for the XYZ title. And then I return two elements, out A and out T, the list of abstracts and the list of titles. Okay. So now that I have walked you through that function, which maybe this was an over explanation, but I just thought it was worth doing that. So I've just run the function, and as you can see, because it returns two elements, and I can directly unpack it into two variables, abstracts and titles. And I can do some verification. So I can take the length of the abstracts variable and the length of the titles variable. And as I hoped, both of them have the same length. So as I said, this is a much smaller version of the original data set, right? Which means that it's going to be manageable. I mean, if we were to process these 5+ gigabytes, this would be massively larger, but for us, it's good enough. Of course, this is going to mean that, you know, these recommendations are probably going to not look great because we don't have that much data to work with. If we had several million papers to retrieve, of course, it would be easier to find a map, a better match that if we only have to do that if we can only do that for a few thousand papers, which might look like a lot, but in fact it's not. And now we can actually see what we have, right? So we've got our titles variable, which is a list, and our abstracts variable, which is another list. We can check the last title and the last abstract, just to recall that we can reverse the indexing with the minus sign. So the title for the last title we have is Genomic Organization and Adaptive Evolution of IGHC Genes in Marine Mammals, and this is the abstract for that. Okay. Right. So now we have text data stored in memory. And now what we want is to turn that text into something that we can compare. And we're going to approach the task as in a kind of standard way that it's done in the NLP literature. Well, standard-ish, it's probably a bit outdated, this approach, but it's good enough. And anything more sophisticated really would require us to look at a bit of theory, probably not the point. So as you may guess, no, it's not like we can throw any type of unstructured data into a machine and it will understand it, no, with italics, no. Of course not. You can throw data and it will probably find patterns because current machine learning models are very good at that. And this is, by the way, this is what we find in all computer vision and language technologies applications. It's very difficult to really expect or to be convinced that what we have is no more than excellent pattern recognition systems. So the way we're going to turn this free text data into numbers is through a process called vectorization, right? So let's have a look. Now we'll spend a couple minutes without looking at any Python code. So for text, well, in general, not in machine learning, and particularly for text, this is a process that's typically called feature engineering. The process of finding representative features, traits in our data that may be good indicators of whatever properties that we're looking for. And for text data, we're lucky because there's a huge body of research on something called representation learning, basically building representations of textual items. And this can, the range of this is massive. No characters, affixes, words, phrases, sentences, documents, you name it. Of course, not only for building recommendation systems, but as the key, like as the cornerstone for any language technology that's built on top of those representations. So what we're going to do is we're going to represent each paper as a vector. So a vector is another word for a list of values, and literally a list, no, with the Python notation. Now what we're going to do is we're going to represent each paper as a vector such that each position, so position 0, position 1, position 2, position 3, position 4, corresponds to one word in a vocabulary. We'll see now where that comes from. And we will write 0 if the word doesn't exist in the abstract, and n for how often we observe that word in that abstract. So 3 would mean that a certain word happens 3 times in the abstract. Because remember that what our code is going to do is going to retrieve the most similar papers to a paper that we already have, based on the similarity in the abstract, not the whole paper, because it would be, well, it would be the same, but to make things a little bit more manageable from the explanation point of view as well, we only operate with abstracts. So we're going to compute similarities between papers based on the abstracts. Now this looks doable. The only problem here is how do we decide? So remember, each position corresponds to one word in the vocabulary, because in this way we can always say the word at position 0 occurs here in this vector, in this paper occurs 0 times, in the next paper maybe occurs 5 times, and so on. But how do we decide which are the words that we include in our vocabulary? So the set of words that correspond to the positions we are going to use in our vectors. Well, typically counting the most frequent words is good enough. So if we look for rare words, even if intuitively they might look like very informative words because they are a very good indicator about the topic of the paper, and therefore I might want to use them. If I represent papers as vectors using word counts, if a word is almost never found in my papers, it doesn't really matter if it's a very informative word, because it will be an informative for those vector representations of the documents, because its value will be 0 almost always. So we actually need to find something which is informative and at the same time frequent enough. And this is where the bag of words representation comes into place. So it's literally like putting all the words in our collection of documents into a bag and then pick one by one and count. As you probably are thinking, well, I can see already a few problems. One problem is there's no order. So I am losing the order when I turn this natural language grammatical piece of text, which in this case is a movie review, into a bag. Of course, I'm losing order, and we kind of assume that order of words is important in language. But that's the approach. That's how it works. And we use this approach to select words from the source documents, put them into a bag, and then count. And then we will put a cutoff threshold. So we'll say, okay, I'm going to keep the 50 most frequent words, or the 100, or the 10,000 most frequent words. And these top K words are going to correspond to the positions in this feature vector. You're probably thinking, well, but there's another problem here. I mean, it, I, the, this is probably very frequent, but this is not telling me anything about the actual content of the review or the paper or whatever. So I need to find a way to prioritize things like whimsical sweet, satirical, which are probably going to tell me a bit more, but are, as I can already see in this toy example, much more infrequent than those which are probably going to be frequent anyway in all documents I have. Okay. So how do we deal with all this stuff? Well, Python. But we actually need to write, unfortunately, a lot of code for achieving this. Hashtag irony. We are lucky, no? Python is the de facto programming language for natural language processing, which means there are a million libraries for us to take advantage from. And this is the first library that we're going to use, and it's time to spend a bit of time speaking about importing libraries and so on. So what we're going to use is, well, one of the features in scikit-learn. So scikit-learn is is described as being a simple and efficient set of tools for predictive data analysis. It's a machine learning library for Python, and as you can see from the front page, we have a lot of software packages from scikit-learn that we can use for classification, regression, clustering, data cleaning. I mean, a lot. Turns out that we can use we can use a package in sklearn called feature extraction, which specifically works for text. And this is the count vectorizer. It's probably self-explanatory what it does. It first counts, and then it builds vectors based on these counts. If this is not super familiar to you, it shouldn't really be too daunting, no? So in Python, we can import external libraries with the import statement, and they allow us to use to have access to code that doesn't come shipped with Python in itself. It wouldn't really make sense to have Python distributions that you download where you have access to everything. You have a basic Python or basic programming language, and then you can use third-party libraries that you can plug into your code. For example, there's a library called collections, which is very convenient. And collections library has one class, one object called counter. And counter is a method that we can use to count things in lists. So here I just imported the collections library, called the counter method from the collections library on this list. This list contains 3 ones, 1, 2, and 1, 3. And the result is a dictionary where I have already counted how many times I find the element 1, how many times I found the element 2, the element 3, and so on. Maybe to make it a bit clearer, let's say 1 and 1 2 times. And as you can see, it also counted the 1 string twice. Okay? So sklearn features this class, which we can initialize like this. We say, okay, I want a vectorizer. So I want to have some piece of code that will go over my papers, and it will turn them into lists of numbers where each number corresponds to where each position corresponds to one word, and each value corresponds to how often that word was found in that particular abstract. And all this stuff I told you about, getting rid of the it, I, the, prepositions, conjunctions, pronouns, and so on. We just do it by passing the argument stopwords equals English. So by default, this count vectorizer will ignore stopwords, which is another word of referring to function words like prepositions, conjunctions, and so on. So by doing this, we already know that our vectorizer will ignore these guys, which is probably a good idea. Lowercase true probably sounds like a good idea, right? Because if I have a million sentences, I would have a million words that start with a capital letter, but I would like intuitively to have those words to be treated in the same way as those words if they happen somewhere else in the sentence where they would be in lowercase. So one strategy is to lowercase everything, then our vocabulary gets drastically reduced, which is also a good idea. And max features. So here we can tell our count vectorizer what is the size of the feature vector, or in other words, where do I put the cutoff threshold here? In this case, I said, well, let's take 100. So let's take the 100 most frequent words in my set of abstracts. After lowercasing everything and removing function words and uninformative words, and this is this object. So this is like a hammer, that this hammer will go through the list of abstracts and will turn each of them into a representation based on the contents in the whole set of abstracts. And this vectorizer object has a method which is called fit transform. So fit means count and define my set of words, and transform means now that I have the vocabulary I want to work with, now take each of the abstracts I have in my collection and transform them into a vector. And with these three lines, I have a variable called capital X, where I have my set of abstracts, 7,000 plus abstracts, converted into a matrix of 7,360 rows, one per document, and 100 columns, one per frequent words, right? X is, if we want to know a bit more, it's a sparse matrix because we have a lot of zeros, right? Because we have a vector of 100 words. They are frequently found words in our whole collection, but it's very unlikely that these 100 words or that a majority of them will appear in all abstracts. So we will have a lot of zeros. So, Python, to save RAM memory, what it's doing is it's keeping track of where the zeros are, but it's not actually storing them in memory. So here it's telling us that it's a sparse matrix, basically with not zeros, with less than 100,000 stored elements. This means non-zero elements. If we want to know how many elements we have in our matrix, we multiply the number of rows by the number of columns. So out of 736,000 components, we have a bit less than 100,000 non-zero elements. And we can call the function get feature names, which actually gets the words that are considered for our feature vectors. And these are the 10 most frequent words that Python found in our corpus, again, after lowercasing everything and removing stop words. And just out of curiosity, so how can we actually measure how much would a matrix, how much space it would take in RAM memory beforehand? Actually, we can, because we know here that it's of type integer 64, so this means 64 bits. So we multiply the number of elements we have in our matrix by 64, and this is going to give us the number of bits we have. But if we divide that by 8, we get this value, which is roughly 6 million bytes, which is effectively 6 megabytes of RAM, because one byte corresponds to 8 bits are 1 byte. So it's quite small. So you could easily store this matrix in a cell phone, and probably a cell phone from 10 years ago. There was a joke back in the day that unfortunately I have to share with you again. If you're from Spain, you probably are familiar with these snacks called boca beats, and well, at least I've heard it more than once. How much, in Spanish, how much are 8 boca beats? So 8 guys of this, 1 boca bite. Silent laughter. Let's move forward. Okay. Right. So we can actually we can actually look at the first row in our matrix. We know that our first paper has 17 non-zero elements, and we are going to store it to a variable first abstract. And this first abstract we can, because you know, it's by default Python will not store the zeros, but we want to actually unpack that and actually see the zeros, because we want to do a little bit of qualitative analysis. So this is the first abstract variable, and we can call the method toDense, where we take the sparse matrix, so with no zeros, stored in memory, and return dense matrix where the zeros are actually represented. And remember that we can retrieve the feature names from the vectorizer. So now we can map each position to the word, and we can actually verify if our code is doing what we expect it should be doing. So let's take the first abstract in our list of abstracts. This guy here. Note this, this is a very neat functionality, but it took me a while to realize. You have to click on the 3 dots here to expand this string. So if this works well, this abstract should have no occurrence of the string 10. Okay? No occurrence for acid and 1 for activity, because it's the third element here and it's the third element here. There you go. No? So we have one token for activity. 1, 2, 3, 4, 5, 6. Let's go to the sixth element. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Anti. Okay, so let's do Control F here. So it says 4, and we have actually 5, but one of them is not, no, because antiviral. No, so anti is a substring of antiviral. So it seems to be working fine, right? So anti, 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 anti. So we have 4 occurrences of the token anti, which seems like a good, seems that this at least exploratory analysis is showing us that this matrix corresponds well with the features that we have, and we are cross-validating that with the actual abstract. Okay. Okay, nice. So now we have again, no, our X variable, which is a matrix of 7,000 plus rows and 100 columns. And now we want to have a way to compare each of these rows to the rest of the rows and get a similarity score. The higher the similarity, the closer each document is going to be. The higher the similarity, the more overlap, so to speak, is going to be between document A and document B, or abstract A and abstract B. So we can take advantage again from sklearn, and this time we can use the subpackage metrics, where we are going to, actually we're not going to use this guy. So these two are to define 2 ways of measuring the distance between points in vector spaces. We're going to use the cosine similarity. For the sake of this tutorial, I thought that we would not spend too much time, or actually any time, on the details of what cosine similarity is. Probably would take a bit long. For our purposes, let's just think of cosine similarity of an equation that takes as input 2 vectors and computes the distance between. It goes from the possible values range from -1 to 1. 1 means that both the vectors corresponding to 2 documents are overlapping, so they're probably the same document. 0 means that there's a 90-degree angle between them, so they're not correlated. And -1 would mean that they're pointing in different directions, so they're negatively correlated. And it's very easy with Python to, once you have a matrix, to build a similarity matrix, where you take, instead of having rows for each document and columns for each word, which you're going to check for each of the documents, what you have is n number of rows times n number of columns. And that's the number of documents, because what you're going to do is compute the similarity between each document with all the rest. And we are going to assign the result of this computation to a matrix K, to a variable K. We can check the shape. So this is not 7,360 times 100, but rather number of documents times number of documents. It's an array of the NumPy type. So NumPy is a package for numerical computations in Python. So basically, all the stuff that we're seeing, the matrices, the sparse matrices, and all these guys, the arrays, these are under the hood NumPy arrays, NumPy objects. They're efficient. It's an efficient library for numerical operations. We didn't look into NumPy, but it's enough for our purposes to know that the outputs that we're getting from sklearn are optimized using the NumPy backend in a way. I think this is a good enough explanation. And here we've got a preview. You see the three dots here. So this is the first rows, and this is the last rows of our similarity matrix. And what we can, and this is the three dots because this is the first elements of the first document, and this is the last elements of the first document. And what we can see, obviously, is that the diagonal is all ones because all papers are equal to themselves, and then and then the values are different, right? So the first paper has a similarity of 0.23 to the second paper, a similarity of 0.13 to the third paper, based on this cosine distance metric computed on top of the count vectorized vectors that we applied in the previous step. I hope this is clear enough. Okay, so now we have everything. We have seen how to take some data, turn it into some Python objects, vectorize them, and building a similarity matrix. Once we have a similarity matrix, it's a walk in the park. The only thing we need to do is for each of these guys, so this is a paper, check where are the highest numbers, basically, because they will correspond to the papers that are most, with the abstracts that are most similar. Okay, and then I write some code that where I am storing the top K results, and then I print them in a kind of nicely-ish way. Okay. So to do that, I am going to write two helper functions, so two functions that I am going to use in my final code. One function is a function called getIndex at position, so of getIndex of one element in one list, because this is going to be useful. And I believed, when I wrote this, that this is more readable than just writing this code inside the paper retrieval system. So this function getIndex will return the position of element I in a list. And if it's not there, it will return none. Because remember that remember nothing. I was going to speak about the void function that they didn't return anything. This function returns the index if the element is in that list. But if the element is not in that list, the function doesn't do anything. In practice, this means that the function will return none. Let's have a look at this. So get index of 1 in 1, 2, 3 gets me index 0, but if I say 4, doesn't return anything. If I assign that to a variable, it's probably none, right? So basically, this function didn't do anything. This code didn't run. And then a function called getSecond. And again, there are other ways to do it in Python with more advanced stuff, but for our purposes, this is important. This is enough. This is a function which, given a Python object, will return the second element. And we will see now why that's important. So if I say getSecond of Luis and Eric, it returns Eric because it will return the second element. Of course, this assumes that what you pass to getSecond always will have two elements, but it will. This will never go wrong based on the code we wrote. Okay? Okay. So what I'm going to do is I'm going to first run the code and see the outputs. And again, disclaimer, don't expect super mind-blowing artificial intelligence stuff here for a number of reasons. Count vectorization is definitely not the best way to extract the meanings of the abstracts, because at the end of the day, we're just looking at overlap between words. We have a relatively small data set, but this was necessary to make everything more manageable. And we haven't really looked into maybe comparing the titles, having a string where we concatenate title and abstract, maybe having the whole paper. There's a lot that could be done and explored. But of course, in the interest of time and making things reasonably understandable, we stick to the simplest approach. So we're going to run the code, we're going to see the outputs, we're going to be relatively satisfied with what we see, I hope, and then I will explain a bit what the code does. Okay, so I am prompted to enter a paper title, and I already know, because I already did some tests, that these are papers for which I have similar papers, right? So I am not going blind. I am not going into the 7,000 plus articles and take random titles and put them there, because it might turn out that the most similar paper to a random paper might be a paper with a similarity of 0.3, which means not similar, and it's going to be a bit disappointing. No? So I know that this guy, for example, has a similar paper, because I already did my research before this. So I'm going to copy this title, paste it here. And this is what my code does. My code says, for paper, emerging infectious diseases with abstract, the spectrum of human pathogens and infectious diseases they cause is continuously changing, And then my results are, wait, this is the same title, but the similarity is not 1. So this means that the vector representations for this paper and this paper, they're almost aligned, but not exactly. So there must be some difference. So if we start reading, let's see if we can spot it. Spectrum of human pathogens and the infectious diseases they cause is continuously changing through evolution and changes, through evolution selection. I found a difference. No, well, I'm pretending, but I already did when I was preparing this. Continuously changing through evolution and changes. This is my query paper. So let's say I have already read this paper and I say, oh, I like this one. So what other similar papers can I see? So my recommendation system would say, hey, this guy is very similar, so you probably like it. It looks like the same paper, but with a few changes. So maybe might be that it was submitted maybe to a conference and then to a journal, or maybe it was an extended version, or maybe there are different versions of the paper, maybe with updated results or amendments. For whatever reason, we have the same paper, almost the same paper twice in our data set, but it's not the same, right? Through evolution, changing through evolution and changes in the way, through evolution, selection and changes. This at least is a good sanity check, because it's really showing that when two papers are almost the same, they will be ranked high. So if we wanted to have a way to measure similarity between papers, this is working. Now, when things get a little bit more difficult and you actually need to get the underlying semantics and the meaning of the paper, then of course things are more complicated, and by counting the number of times the words in a predefined vocabulary, this is not going to be the optimal way, but it's a way. Our second best recommendation is this guy, Role of India's Wildlife in the Emergence and Re-emergence of Zoonotic Pathogens. Questionable. And this is 0.77, almost 0.78, which, you know, I've done a bit of vector space representation of that. This is not bad, really, but still, it's not. So this means that the representations that we have, the vectors that we have, probably are not optimal. Okay, so let's have a look. No, so one way we could actually verify how they are related, well, we could do Control F here and maybe check, no, is there a qualitative way for us to see if there's any overlap between them? So can we, I don't know, let's say disease. So I can see that my query paper has the word disease, this as well. So I am assuming here that I have an entry in my document vector for the token disease. This means that for this token, they are similar. Yeah? I have one in one paper, one in the other. So in this coordinate in the vector space, I have a match. and so on. No, so this is the wildlife. Turns out the third paper is very similar, and it's also about ecology of wildlife diseases. So, and this actually, the query paper is about an animal reservoir. Let's have a look at the word wildlife. What do we have here? Wildlife. So this is interesting, right? Because this query paper at least mentions animal reservoirs, but doesn't have the word wildlife, which appears in the second and third best recommendations. This points to something which, if you're curious about how this could be improved, this points to a phenomenon called the distributional hypothesis, right? And what this is saying is, what we can infer from here is that this paper speaks to a certain extent. I haven't read the abstract in detail, but it does speak to a certain extent about animal reservoirs, wildlife, and animals in general. No? So if I don't have the word wildlife here, I never have a match between the query paper and all the others because I don't have the wildlife here, and I am assuming animal reservoir. So I have animal reservoir here, but I don't have it here. So some papers have wildlife, some other papers have animal reservoir. In practice, in our similarity computation, this is 0 because those vocabularies are not the same. But for us, wildlife and animal reservoir are similar words. They're similar concepts. At least they are more similar than wildlife and rugby, or animal reservoir and, I don't know, a cake. So would it be possible to actually encode the fact that animal reservoir and wildlife are similar so that in this case I can see it because anyway they are ranked high? But what if I have other papers with even less overlap and in terms of actual words, but they speak about the same thing? So long story short, yes, this is an area of research where you would learn vectors for these individual words such that wildlife and animal reservoir are close in the space themselves. So instead of having one number for each word, you have one vector, and then you can do a lot more cool stuff with them. Okay? Okay. So time for code. This code, what it does is it takes as input a string, which is going to be our paper title. And I already knew that these guys were quite promising, so I just copy paste it. Then I call the getIndex function of the paper title on the titles array, the list of titles. So this is going to give me the position. So because I have already run this code, I have the values for these variables stored, so I can actually check the index. So this emerging infectious diseases paper is the paper at position 103 in my titles list, in my abstracts list, and also is the row 103 in my matrix for count vectorization and my similarity matrix. Everywhere is the same position. That's why we loaded our data as lists and not as dictionaries, to have a way of, with one single number, we can access title, abstract, all the similarities for that single paper and the vector for that paper. So these are some print statements. Here, if paper index, because it might be the case that I don't have that paper, maybe I write a typo or something. So if paper index is not none, and so this is another way of writing the same, run this code. If it's none, then just print the paper was not found and leave, and don't do anything else. Okay. Now for paper which is the retrieved title for that index 103, and with abstract, the abstract paper index with this abstract, and now I print the results. Probably not necessary at this point. Now, what I'm going to do is I define a similarity list, which is going to be empty at the beginning. And now I'm going to iterate over all the positions in my similarity matrix, but only for the row that corresponds to that paper index. So effectively, I have paper 103, and then I have similarity 0.4, 0.75, 0.1, 0.00 something. Then at position 103, it's going to be 1 because it will correspond with itself, and then other similarities. So I am going to iterate over all the positions here. So this notation basically means get me all the positions of this list. So let's say I have a list of 2, 4, 6, 8, 10. And for position in range of the length of this list, print the position. Range for I in. Right, so this bit of code, the only thing it's going to do is print how many positions do I have. But this is useful, right? Because this position variable, which is the same as this I position in this toy example, I can use it to retrieve the similarity for paper 103 at position 0. So the first paper, the second paper, the third paper. And I have the similarity retrieved by accessing the matrix. So the first element here, this gets me the row. So the row at that position. And once I have that row in that matrix, I am going to iterate over each of the positions of that row, or in other words, list. And then I append to the similarity list a tuple where I keep track of the position of the paper and the similarity. And as a sanity check, let's have a look at the first 10 elements in our similarity list. Right? So this is the list of papers, the first, the second, the third paper, and the similarity to paper 103. And now what I do is called the sorted method, which is something that already Python does. If you're planning to go into a programming interview, you probably need to learn about many different algorithms for sorting. But because Python has this already built in, we don't need to do it ourselves. We can just call. So if I have a list 4, 3, 4, 5, and I say sorted, so sorted. And if I say reverse equals true, well, it reverses the order, so not bad. So I am doing that. I am getting an ordering of my similarity list, and remember that the similarity list is a list of tuples with paper IDs and similarity. But according to what do I order them? The first element, the position? No, I want to order them by similarity, and I want to keep the highest first. So this is why the sorted method accepts a key optional argument where I can tell it the key. So what does the sorted function need to look at for sorting the array? That's where my getSecond function comes into place. I pass a function such that for each element, it will sort by the output of this function. So effectively what this does is sorting by second element, or in other words, sorting by similarity. And now I have all the papers sorted by similarity, but of course the first paper is going to be that same paper because that similarity is going to be 1. So I want to skip that guy. That's why I am not retrieving everything. I'm going to retrieve from the first element to the fourth. So this means skip the first one and keep the next 3. And that's it. And this is then sorted sims is a list of tuples where the first element of that tuple is the paper index, and the second element is the similarity with paper 103. And then I print, and done. And this has been my recommendation system. And we could try other. So let's try, for example, hello world. Paper not found because we don't have any paper with that title. Done. If we wanted to know, if you're curious, how did you find these guys? did you went manually paper by paper and check? No. What I did, there's a bit of code here. What I did was simply iterate over all papers and keep those papers for which I had a similarity above something. And instead of doing this kind of convoluted Python code here, I use the pandas libraries, which is a library for data processing. You can do the same in one line, but in the end, the result is the same. It's a list of rankings where the rankings correspond to the similarity between your query document and the rest of the target documents. And that's it. That's how you implement a. Perhaps you may like these guys. So yeah, not bad. Timing wise, I guess we could take 1 or 2 questions if they're quick.
Yeah, definitely. I don't know if you can see my camera now or not.
Yep.
Okay, cool. So yeah, the Q&A was there the whole time. So if somebody else wants to make a question, this is the time. Anybody?
Well, it was while you consider whether you have something to ask or just. I hope it wasn't too overwhelming. I try to make it. I try to make it as accessible as possible and giving as many details as possible. That's why it's not very sophisticated, because there's a trade-off between how much complexity you can add and explaining all the details in the development process. Of course, this notebook will be online. The only thing that you need is for it to work is access to Google Drive and actually these 2 files. So we might as well upload them too. So you have the same data that I used for loading. The difference would be that this data directory would be different in your case, because of course you would store them in a different folder than me.
That's fantastic. Thank you so much, Luis.